For this course, we introduce the mathematics that form the foundations of many machine learning methods. The hope is that you're able to learn the rudimentary forms of the language of mathematics from these first videos. We'll now use these to describe and discuss machine learning. In the upcoming videos, we'll talk about regression, dimensionality reduction, density estimation, and classification. You always need to consider the problem that a machine learning algorithm is designed to solve. When doing this, we need to consider the three major components of a machine learning system: the data, the models, and the learning. The main question in machine learning is, what do we mean by a good model? The word model has many subtleties, and we'll revisit it multiple times in this sequence of videos. It's also not entirely obvious how to objectively define the word good. One of the guiding principles of machine learning is that good models should perform well on unseen data. This requires us to define some sort of performance metric, such as accuracy or distance from the truth, as well as figuring out ways to do well under these performance metrics. We assume that our data can be read by a computer and represented adequately in numerical format. Data is assumed to be tabular, as it is in both these tables displayed here, where we think of each row in the table as representing a particular instance or example, and each column to be a particular feature. In recent years, machine learning has been applied to many types of data that do not obviously come in the tabular numerical format. For example, genomic sequences, text and image content from a web page, and social media graphics. Even when we have data in a tabular format, there are still choices that have to be made to obtain a good numerical representation. For example, if we look at the top table, the gender column is in terms of M and F. This could easily be converted to numbers where 0 represents male and 1 represents female. Alternatively, as in the bottom table, the gender could be represented by numbers negative or positive 1. Furthermore, it's often important to use domain knowledge when constructing the representation, such as knowing that university degrees progress from bachelor's to master's to PhD, or realizing that the postal code provided is not just a string of characters, but actually encodes some area in the world. We took the top table and converted it into a little bit more tidy format in the bottom table. We took each postal code and represented it by two numbers, a latitude and a longitude. Even numerical data that could potentially be directly read into the machine learning algorithm should be carefully considered for units, scaling, and constraints. Without additional information, one should shift and scale all columns of the data set such that they have an empirical mean of 0 and an empirical variance of 1. For our purposes here, we assume that the domain expert has already converted the data appropriately. That is, each row is a d-dimensional vector of real numbers, which are called features, attributes, or covariates. We assume the data set to look like the bottom data set. Notice that in the second table, we've dropped the name column. There's two reasons we may want to do this. One, we do not expect the identifier to be informative in our machine learning task. Second, we may wish to anonymize the data to help protect the privacy. As a convention, we will use capital N to denote the number of examples in a data set, and we'll index examples by a lowercase n. And we assume that we're given a set of numerical data represented as an array of vectors, as in the second table. Each row is a particular individual, xn, often referred to as an example or a data point in machine learning. Subscript example n refers to the fact that this is the nth example out of a total of capital N examples in the dataset. Each column represents a particular feature of interest about the example, and we index these features with a lowercase d. Recall that data is represented as vectors, which means each example or each data point should be a d-dimensional vector. Let's consider the problem of predicting annual salary from age based on the data in the previous table. This type of problem is called a supervised learning problem because we have data labels, yn, the salary, associated with each example, xn, the age. The label, yn, has various other names, including the target, the response variable, and the annotation. A data set is written as a set of example pairs, x1, y1, x2, y2, xn, yn. And the table of examples is often concatenated and written as capital X in R n times d. We want to use the concepts that we've talked about in previous videos to formalize machine learning problems such as this one. Once we have data in an appropriate vector representation, we can get to the business of constructing a predictive function known as a predictor. Talk about two major approaches here: the predictor as a function and the predictor as a probabilistic model. A predictor is a function that, when given a particular input example, in our case a vector of features, it produces an output. For now, we'll consider the output to be a single number, that is, a real valued scalar output. We can write this as f going from Rd to R, where the input vector x is d-dimensional, or has d features, and the function f that applied to it, written as f of x, returns a real number. We often consider data to be noisy observations of some true underlying effect, and hope that by applying machine learning, we can identify the signal from the noise. This requires us to have a language for quantifying the effect of noise. We often would like to have predictors that express some sort of uncertainty. For example, to quantify the confidence we have about the value of the prediction for a particular test data point. As we've seen, probability theory provides just such a language. Instead of considering a predictor as a single function, we could consider a predictor to be a probabilistic model. That is, a model describing the distribution of possible functions. The goal of learning is to find a model and its corresponding parameters such that the resulting predictor will perform well on unseen data. There are conceptually three distinct algorithmic phases when discussing machine learning algorithms: prediction or inference, training or parameter estimation, and hyperparameter tuning or model selection. Prediction phase is when we use a trained predictor on previously unseen test data. In other words, the parameters and model choice are already fixed, and the predictor is applied to the new vectors representing new input data points. We will consider two schools of machine learning here: corresponding to whether the predictor is a function or a probabilistic model. When we have a probabilistic model, the prediction phase is called inference. Training or parameter estimation is a phase when we adjust our predictive model based on the training data. We would like to find good predictors given the training data, and there are two main strategies for doing so: finding the best predictor based on some measure of quality, sometimes called finding a point estimate, or by using Bayesian inference. Finding a point estimate can be applied to both types of predictors, but Bayesian inference requires probabilistic models. For the non-probabilistic model, we follow the principle of empirical risk minimization. Empirical risk minimization directly provides an optimization problem for finding good parameters. With a statistical model, the principle of maximum likelihood is used to find a good set of parameters. We can additionally model the uncertainty of parameters using a probabilistic model, which we'll look at in more detail in a future video. We use numerical methods to find good parameters that fit the data, and most training methods can be thought of as hill climbing approaches to find the maximum of an objective. For example, the maximum of likelihood. To apply hill climbing approaches, we use the gradients and the numerical optimization approaches we've seen in previous videos. Since we're interested in learning a model based on data, we need it to perform well on future data. It's not enough for the model to only fit the training data well. The predictor needs to perform well on unseen data. Simulate the behavior of our predictor on future unseen data using cross-validation. As we'll see, to achieve the goal of performing well on unseen data, we need to find a balance between fitting well in the training data and finding simple explanations for the phenomenon. This trade-off is achieved using regularization or by adding a prior. We often need to make high-level modeling decisions about the structure of the predictor, such as the number of components to use or the class of probability distributions to consider. The choice of the number of components is an example of a hyperparameter, and this choice can affect the performance of the model significantly. The problem of choosing among different models is called model selection. For non-probabilistic models, model selection is often done using nested cross-validation. We also use model selection to choose hyperparameters for our model. In our next video, we'll spend some time talking about empirical risk minimization.